Welcome back. We are closing in on the last new content for Unit 1, and we are going to wrap up these ideas with normal models, calculating area under the curve, and identifying if things are unusual or not. So last we were doing a little bit of calculator work, and we were finding area underneath the curve of a normal model. Well, what happens if you're given a percentage and you're asked to find a z-score? So sometimes we start with area and we need to find the corresponding z-score or the original observational value. So for example, what z-score represents the first quartile in a normal model? Now I say that, and Q1 is the 25th percentile. We know that. So if we drew our standard normal model, where would 25% be? What would be the normal model? Well, what we need to do is if we wanted to do it in reverse, we could go to our table and we can find the area in our distribution on where we have approximately 0.25. And because if we see it's 6, 7, 6, 8, 0.25 probably falls somewhere in between. So this figure, if we were using our table, is associated with this, a percentage of 25% is associated with 0.675, negative 0.675 z-score. So the first quartile is about 0.675 standard deviations below the mean. Notice that negative implies below, B-E-L-O-W, just means negative z-score. Well, how can we do that using our calculator? Well, to find a z-score corresponding to area, or to know that what z-score lies above or below a given percentage, the idea is to simply work backwards. In the table, you first find the percentage in the field of the table, then determine the score by combining the row and column headings. Well, that makes sense. So to find a z-score below which falls 72% of the scores, or the 72nd percentile, we would need to locate this 0.72, and then we see that it was 0.5 and then 0.08. So if we put those two together, we get 0.58. But again, why are we using a table when we have this technology in advanced? So again, we're going to hit menu in a calculator. We're going to go down to statistics, and then we're going to go down to distributions. And this time, instead of normal CDF, we're going to do inverse normal. And inverse is the opposite or backwards operation of what we just found. So it prompts you the area, 0.72, below, our mean is 0, our standard deviation is 1. So if we do inverse normal, we get a much more precise value than we did with our table. So we get 0.582841. And you can see much more accurate and quickly of just typing in the area, the mean, standard deviation, hit enter. For those on your TI-84, you hit second vars, which gets you to your distributions. And then you go down to the third option, which is inverse normal. And you'll get the exact same operations. Likewise, remember, the TI-84, the TI Inspire, requires the area below the desired score. So if you're given the area above, you must subtract from 1 to find the area. That concept is called the converse. So to find the z-score above, which falls 25 or above 25% of the scores, which would be finding how much area is above the third quartile, what we would first start with is inverse normal. So we go menu, statistics, 5 for distributions, and then inverse normal. Our cut line, if we drew this picture, we want to see what is above 75%. So if we go 0.75, 0 to 1, great. And then I'm going to do 1 minus, and I'm just going to scroll up to that answer and hit enter, and then enter one more time. And we see that we get 0.3255. We already knew that 25% of the normal model was 0.67. The reverse of that is going to be 0.32. So when you have your own data, you must verify whether a normal model is reasonable and appropriate. AP and I will require you to verify the appropriateness of your methodology by ensuring the data distribution is sufficiently unimodal and symmetric. So of course, you could look at a histogram of the data, which is our sample, is probably the best way to check that underlying distributions is sufficiently unimodal and symmetric. Another graphical way that can help you determine whether a normal model is appropriate is the normal probability plot, or we call that the NPP. In essence, if the distribution of data is roughly normal, the normal probability plot approximates a diagonal straight line. Significant deviations from the straight line indicate the distribution is not normally distributed. So, to create a probability plot, which is what your calculator is going to do, you would first have to order the data, then calculate all the percentile, then find the z-scores in the matching the calculated percentile. Plot those points with the x to the y, where zx is the score calculated for the observation and zp is the score corresponding to the percentile. And then we would check for linearity. Got all that? Great. I will never ask you to do that by hand. So the much better way to create a normal probability plot is to let the calculator do it for you. Now, if you're on a TI Inspire, you hit Stat Plot, then choose the last icon, which looks like a line, and then you select your data, which you want either the X or Y axis, and then you'll hit Zoom 9. If you are using your TI Inspire, all you have to do is instead of select histogram, you are going to select NPP, or normal probability plot. Let's say we're doing math anxiety. Okay, so this data you don't have, but I just wanted to show you. If I went to Control Doc and I added a data and statistics, and I'm just going to graph math anxiety level. And we can see that our data is roughly symmetric and unimodal, roughly. If I want to switch that from a dot plot to a histogram, I just select 3. If I wanted to select a normal probability plot, I will then transfer this to a line. And what we are looking for is to see if this is sufficiently, all of the dots fall along our line, and we don't have too many outstanding features. Back to our notes, for using a normal probability plot, the nearly normal data have a histogram and normal probability plot that looks somewhat like the example of 100 values of randomly sampled from a normal distribution. So we can see our normal probability plot generally falls along this linear function. That tells us we are approximately symmetric and unimodal. If data sampled from a left skewed distribution, so we see that this is a left skew because the tail is on the left, you can always draw in the whale, we see that our curve, or our line, is going to dip down further to the left. Likewise, if we have right skewed data, draw our fantastic whale, we are going to similarly see at the end, or the right side of our normal probability plot, this kind of curve upwards. So when we are looking at either a histogram or a normal probability plot, or both, this allows us to check for symmetric unimodal data, which is what we want. So here is our last question. I'm going to read it to you, and I'm going to pause the video, and I'm going to ask you, try this problem out on your own. So suppose a vending machine dispenses hot beverages into 8-ounce cups. The machine is set to dispense with a standard deviation of 0.2 ounces. So you would expect you could get, on average, you get 8 ounces, but maybe you get a little more, maybe you get a little less. Providing too much beverage risks burning the customer. Not a good thing. Providing too little beverage risks frustrating the customer. So we say that the standard deviation of this population for this machine is 0.2. What mean setting do you recommend for the machine? If we want to keep the vast majority of customers happy, we should ensure that 95% of our customers get at least 8 ounces. So we want 95% of our customers getting at least 8 ounces. What does that look like? Okay, so if we want to keep the vast majority of customers happy, we should ensure that 95% of our customers get at least 8 ounces. Well, that means that only 5% are not getting what they want or are underneath. So we're looking for our mean. We know 0.05 would be lower than 8, and everyone else would be above. Note we are given our standard deviation, so what we are going to start with is getting a z-score. What we do, just like we did before, is we open up a calculator. We start with 0.05, which is the percent of people not getting what we want. And we're going to use our standard normal model to get a z-score. So if we wanted to, we are on a calculator page, we would hit Menu, 6 for Statistics, Distributions, and then we go Inverse Normal because we have a percentage, 0.05. This is the amount of customers that are not getting what they want. We get a z-score of negative 1.6448. To find the mean, we have to convert the z-score to an actual value. So remember, z-score is observed minus the mean over the standard deviation. Well, we just found the z-score from our calculator. Our actual data point is 8. That's what we want 95% of our customers to get. We're looking for the mean, and our population standard deviation is 0.2. So if we cross multiply and then switch the number with mu, we will get 8.3290. So to ensure that 95% of the customers get at least 8 ounces, the machine should be set with a mean of 8.3290 ounces. Note, 4 decimals. Well, the company is not happy with our recommendation of 8.329 ounces because that's going to cost too much money. We must come up with another recommendation to ensure that 95 customers get at least the full 8 ounces. What is the difference there? So of course we could lower the mean volume to 8.1 instead of 8.3, but that would leave a lot of customers unhappy. What percentage of customers would get cheated? Well, if we're figuring out percentage, we're doing normal CDF. So on our calculator, if we want to figure out how many customers, if our mean was, our lower was 8 and our upper was 8.1, we're going to hit Menu, Statistics, Distributions, Normal CDF. Okay, so our lower bound would be 8. Our upper bound, our lower bound would be, let's say, negative 10, because we just want everything below there. Our upper bound would be 8, with our mean being 8.1. Notice we've changed it now, and our standard deviation to be 0.2. If we do that calculation, 30.85% of the vendor's customers would be shorted if we just drop the mean to 8.1, and that's too much. Okay, so naturally, the company is not pleased. The 8.1 ounce is acceptable to the company, but the percent below 8 is much too high. So you cannot seem to make some people happy. So what else might we do to make the company and the customers happy? Okay, so we could recommend the company produce vending machines that are more consistent in their distribution. If we're talking about more consistent, we're talking about a new standard deviation. So if we are asking for more consistent, that means we are reducing the variability in the data. If we are reducing the variability, we are changing the standard deviation to ensure that 95% of the customers get at least 8 ounces with a mean of 8.1. So this is our formula. We already know the z-score that we calculated in the first part. This is a z-score with a inverse normal of 0.05. So 95% of the customers are getting at least that amount, 0, 1. So we got that negative 1.6449. This is our value minus our mean, and then we're finding the new standard deviation. So again, I trust you to do this calculation. And so if we are reducing the variability, instead of having the machine spit out 0.2 ounces plus or minus, if we have it spit out 0.0608 ounces, the standard, that would reduce the variability and make the company happy and the people happy. So from this point forward, it will no longer be sufficient to simply find the requested values. You must conclude every problem with a concluding sentence. So we found the standard deviation of 0.0608. So our concluding sentence would be something of this order. To ensure 95% of our customers receive at least 8 ounces with a mean of 8.1, the standard deviation would need to be changed to 0.0608 ounces. That is Unit 1. We've talked about what does data look like. We have talked about statistics being the study of variability. We talked about categorical data and how to graph it. We've talked about quantitative data. If the data is skewed, if the data is symmetric, how do you describe data distributions? You have to remember your socks. We have now looked at box and whisker plots to analyze the 5-number summary, usually for skewed data. If we're looking at skewed data, it's median and IQR. If we're looking at relatively symmetric unimodal data, we are looking at the normal model. So I look forward to seeing all of you guys in class to talk about normal models. We'll do a couple more activities, and then otherwise we are at the point where we can test for Unit 1. So thank you for sticking with me, and I will see you guys later. Good luck, Falcons.